I think I'm the first Tuzo Wilson lecture introducer who didn't ever know or meet Tuzo Wilson. My impressions of him are therefore entirely based on his work, what's written in textbooks, and what people say about him. One thing I've noticed is that as soon as you bring up the name Tuzo Wilson to someone in the department who knew him, their face immediately lightens up and they want to tell you stories about him, about their interactions with him. I think this is truly revealing of the impact he had on our community, not only scientifically, but also personally. And I don't think one can ask for much more out of life as a professor and scientist. In honor of Tuzo Wilson, the Department of Physics created the J. Tuzo Wilson Professorship in Geophysics in 1995. The position is appointed for 5 years to a prominent U of T professor who has made significant contributions to the field of geophysics. This year marks the incoming of Professor Stephen Morris as the new J2 Wilson Professor, having succeeded Nigel Edwards after his term. The first year of the term is marked by having the Tuzo Wilson Professor give the Tuzo Wilson Lecture, and I'm therefore happy to introduce Professor Stephen Morris as this year's lecturer. I first met Stephen when I was an undergraduate student in physics here. He gave a guest lecture to my third-year lab class on something called spiral defect chaos. At the time, I thought there's no way something that cool actually exists. During that lecture, not only did he demonstrate that it does exist, but that you can build a tabletop experiment to show it. Stephen's work covers a vast array of physics topics with the underlying theme of pattern formation. A quick glance at his website will deliver project topics such as the fluid mechanical sewing machine, the shape of icicles, washboard road, and a supernova in a jar. He received his PhD from U of T in 1991 and has been a professor here since 1993. He was awarded the Faculty of Arts and Sciences Outstanding Teaching Award in 2004 and was named a Fellow of the American Physical Society in 2012. You've probably seen him in his work on the Discovery Channel, YouTube, or Flickr, where he regularly demonstrates exciting physics phenomena to a broad audience. Today, we are going to hear about his work on an amazing geological pattern known as the Giant's Causeway. Please join me in welcoming Professor Stephen Morris.
Thank you. Thank you. Thank you. Don't clap. I haven't said anything yet. We're feeding back. Sound booth. Oh, wait. I got to turn this on. It's great to be here. I actually did meet Tuzo Wilson once. Back when I was a graduate student, we used to have a graduate student-only seminar series on Friday afternoons at 4 o'clock because we knew that no professors would ever come at Friday afternoon at 4 o'clock. And we had 2 cases of beer that we kept on the front counter, and the speaker was allowed to start drinking the beer while they gave their talk, and everyone else had to wait until he finished speaking. And somebody had the waggish idea to invite Tuzo Wilson to give a graduate student seminar at age 84 or 85, something like that. And I vividly remember standing at the front of the room and making a little speech appointing Tuzo Wilson as honorary graduate student for the day, in order so he would be qualified to give the graduate student seminar. And then I handed him his beer. So that was the one, unfortunately, the one and only time I ever met him. And he gave a very spirited talk on plate tectonics. And I wish I'd taken a picture or something in those days. One didn't take pictures. But if you told me then that I would be standing here giving the J. Tuzo Wilson Professorship lecture, I simply wouldn't have believed it. It's unbelievable. It's unbelievable. So I'll tell you another little story about my interaction with Tuzo in a second here. I'm going to get my talk up. I'm going to tell you about rocks, okay? It's useful to remember that geophysics is ultimately about rocks. In this era of wonderful satellite data and planetary geophysics, it's nice to know that just plain old garden variety rocks are still interesting. These are just not any old rocks, of course. These are probably the most famous rocks in the history of geology. This is the Giant's Causeway in Northern Ireland. And this is a tabletop experiment, which I will show you a little bit later. And I hope I can convince you that there's some connection between these two things. But I wanted to show you the book that got me into this field, okay? It's called The How and Why Wonder Book of Our Earth. And it was published in 1960. And I must have received it around the time I was born in 1959, or I must have received it soon after. because I don't remember any of the words of this book, but I remember every single picture in this book. So I believe I received this book as a kid before I could read. And who could not be fascinated by a cover like this? It's got everything, right? It's got cracks. So subliminally, I think I saw this. It has always been in the back of my mind. But if you go to page 19 of this book, and I vividly remember these pictures, there are these fascinating things like here's us, right? And here's the geologic timescale. And there's this funny picture with the blob between the two continents here. And if you read the section here called What Was the Earth Like Long Ago, it talks about now we've studied fossil clues, and we've discovered that at one time a bridge of land probably connected northern Europe with Greenland. And another such land bridge extended between Spain and the United States. And at still another stage, Africa and Australia and South America were all part of the same mass of land. And forests of fern trees grew across what are today thousands of miles of open water. And, you know, here it is. There's the lost continent there. And, of course, this is what Tuzo Wilson did for us. He eliminated those thousands of miles of fern trees by the simple expedient of putting this one up against that one and having the ocean disappear in between them. And so this was 1960. Within about 10 or 15 years of this book's publication, this became a chuckleable idea. But that's sort of where I came in, I guess. I don't remember these words, but I sure remember these pictures. And I remember the lost continent of Lemuria, where the lemurs come from. It's in the middle of the Indian Ocean. It's not really there. But anyway, I gave this book to my kids, but I don't think they actually looked at it. But anyway. So I'm going to talk about the work of several people. Almost everything I'm going to tell you about was the thesis work of Lucas Göring, who's now a group leader at the Max Planck Institute in Göttingen, and my summer student Mary Miedema, who has made an interesting film which I'll show you, and myself. And we had some theoretical help from Mahadevan from Harvard. And Mahadevan's great ability is to make complicated things really, really simple. So he gave us the courage, if you like, to believe that we'd actually had a very, very simple argument that I'll give you about these columns. And here's Lucas at work on his thesis. He's wearing a life jacket because if he falls off here, he'll land in the surf. And he's wearing climbing boots and a hat because if he falls off, he'll bang his head. And he is actually climbing not the Giant's Causeway, but another place that I'll tell you about. So here's probably the most famous picture that people see about the Giant's Causeway. If you go there, how many people have been there? Oh, a few. Okay. It's a World Heritage Site. It's on the north coast of Ireland, and it basically faces north. It's at the bottom of a huge cliff, and it's a huge array of spectacularly, weirdly ordered rock columns, and they all fit together like pencils. And they're mostly hexagonal, but they're not all hexagonal, but people often say they're all hexagonal, and there's thousands and thousands of them, and they're sort of in the surf, and it's a very dramatic sort of place. The real trick when you go there is to take a picture with no people in it, because as a World Heritage Site, it's crawling with tourists all the time. And so I had to wait for a gentleman to walk down behind that little mound before I took this picture. Scientifically, also, it goes back right to the very beginning of science. In fact, not just to the beginning of geology, but really to the beginning of science. It was first reported to the Royal Society in 1693. And I can tell you that because you can download the paper, okay? It's on JSTOR. And it's published in Philosophical Transactions of the Royal Society. And it's written by Sir R.B. SRS. In those lovely far-off days, gentlemen scientists were so chummy that they didn't even have to put their names on their publications. And for a long time, we had no idea who Sir R.B. SRS was. And eventually it was tracked down. His name is Sir Richard Bulkeley, Scottish Royal Society is what it actually stands for. And like a good gentleman, he didn't personally go to the Giant's Causeway because that was not what gentlemen did at the time. He reports the tales of travelers. So first he tries to convince the editor that, I'm sure you'll pardon, I was very exact in getting it from a person that was re compos and perhaps peritus, a scholar, a master of arts from Cambridge. So in those days, gentlemen, especially gentlemen who were interested in geology or geography, they didn't go away from their comfortable armchairs. They sent men out to bring back a rock or maybe to send back a verbal report. And so the idea that geologists or people of that sort should be interested in actually going to the field took more than 100 years to become common. As far as they were concerned, the Giant's Causeway was a thing that they could trust. If they trusted the reports from the travelers, that's all they needed as far as data went. Today, this formation is called columnar joints, and the Giant's Causeway is by no means unique. In fact, it's found all over the world. I'll show you a few examples. The word joint does not mean what people in my generation think it means. It means a crack which does not slip, okay? So it's just a crack that opens. So columnar joints refers to the fact that these things are formed by a cracking process. Basically, and I'll describe this in gory detail, but a lava flow came down some tens of millions or 60 million years ago, and as it cooled, it cracked into this strange pattern. So here's a picture of the Giant's Causeway taken from the top of the cliff, and you can't really see it, but there's thousands of these little, mostly hexagonal things all over here. The little mound that I showed you is just this little bump here. And I will draw your attention to this wall here. It's sort of a ramp with a wall on the other side. And or I should say, it's very difficult to get a sense of this thing without being there and walking around. It's almost impossible to take a picture of lots of joints at once without going to the top of the cliff. But this picture was taken in a very clever fashion. Can anyone guess? It looks like a drone picture, right? And indeed, if you put Giant's Causeway drone in, you can find beautiful videos. But this was made in an even cleverer fashion from a kite, okay? So this guy, Nick Russell, went to the Giant's Causeway and took a number of wonderful pictures by kite. So this is very good illustration because you can see what you would see sort of walking around. Here's a person from scale. These things are mostly hexagonal. Some of them are extremely hexagonal. Here's a very good one up here. And some of them are really rather far from being hexagonal. Here's a kind of, block-shaped one here. These little things are actually puddles, and so some of them dome up and some of them dome down. And I'm not going to talk about that. That's called the ball and socket joint. I'm talking about the cracks that separate the little tiles from each other. Those are the things that are the subject of the talk. And there's thousands and thousands of these columns at the Causeway. So here's a picture taken from the cliff a little bit farther east, and here's that wall that I pointed out to you before, and here's the actual Causeway. And I will spare you the story of the giants, okay? Every tourist is told a complicated story of a battle between a Scottish giant and an Irish giant, and it's really hilarious, but that's, of course, not actually how they formed. So to get back to the history, the reason that outcropping there is so famous is that it prominently appears in this picture, which is one of the first accurate illustrations of a geological topic ever made. In fact, the picture that precedes this was actually commissioned by the Royal Society. It was the first effort by anyone to draw a realistic picture of a geological formation for the purposes of learning something about science. And this is like the second one. And some people believe that Susanna Drury, who's a no-name artist, no one knows anything about her, some believe she used a camera obscura to make this picture. It's so realistic. Or she also had to populate it with little groups of happy landscape figures in order to kind of make it a friendly scene. And one of the reasons it's extremely influential and famous was because it was quickly engraved, actually some years, but it was engraved in this engraving. And it's interesting to see what the engraver thought was important and what they left out. So if you look at the details, you can see the rocks move around a little bit between the two pictures, and the people are looking in different directions. But after it was engraved in 1744, it was published a little bit later in the famous encyclopedia put together by Diderot and d'Alembert. And it was the result of this very wide dissemination of this picture of the Giant's Causeway that it became a famous sort of uncanny thing that had to be explained. And it was only after seeing pictures like this that people began to realize that there were other places where rocks were broken into these amazing columns. There's some in the center of France, for example. And that began the kind of the widespread understanding that this was an interesting place. It was a little bit of a tourist trap before that, but after this, it became a major tourist trap. So it's been a tourist trap for 250 years or whatever. Okay, so here is my friend Bob. And Bob Mayhew, you're going to hear more about him later, but here he is sitting on top of that very outcropping that I showed you a minute ago. He didn't actually climb up there. He actually went up the back, which is much easier to do. So the Giant's Causeway is by far the most famous example of columnar jointing, but probably the second most famous example is an island near Mull in the Inner Hebrides of Scotland, which is just across the Irish Sea from Northern Ireland, where the Giant's Causeway is. And it's called Staffa, and Staffa is an ancient word meaning a stave, like a post for your house. And the Staffa is, if anything, way more spectacular than the Giant's Causeway. You don't need to wander around on it to appreciate it. You can see it from a boat. and it has this spectacular colonnade, which is like a layer cake of beautiful ordered columns. And these are actual people for scale. They're not 17th century tourists. They're real tourists, okay? And you can see the very, very, very regular columns there. Dr. Johnson, Samuel Johnson, actually managed to, in the 18th century, to visit both Staffa and the Giant's Causeway, and he famously said of the Giant's Causeway that it was worth seeing, but not worth traveling to see. So, which is a nice put down, a very British sort of thing. The reason why you may have heard of Staffa is because just to the right of the picture I just showed you is a spectacular wave cave, which is dug into the columns by wave action, and it's Fingal's cave. And of course, it's famous because it was visited by Mendelssohn, who actually didn't get out of his boat, but he went to there and was so impressed by the sights that he wrote a part of the Hebridean Overture, which is called Fingal's Cave. And those of you who are musically inclined can, whistle it to yourself in your head. I don't really know what it sounds like. But Fingal's Cave brings in Bob Mayhew, because Bob Mayhew is a spelunker. And at the time I met him, he had a permit from the Scottish National Trust, who owns Staffa now, to survey the caves of Staffa. And as you'll see, there are quite a few caves. And so he got interested in columnar joints, and we started working a little bit on columnar joints together. If you go inside Fingal's Cave, you can kind of walk right in, and there's a beautiful sort of pathway on the stones here. It's an unbelievable sight. The waves roar right back, and they crash right at the back of the cave, and then they roll back out again. And the far side of Fingal's Cave looks like this. It was described in the 19th century as a kind of natural cathedral, and it fitted in perfectly with the kind of natural theology of the day. How could such a beautiful piece of work not be, the work of the Creator and so on? There's no scale in here, but these things are about half a meter in size. Here, by the way, is an engraving of Fingal's Cave, which shows you that some engravers are much more careful about their engravings than others. And this is not a particularly realistic picture of Fingal's Cave. Now, columnar joints, the reason that Giant's Causeway is famous is partly just because Englishmen visited it. Once you start looking for them, you find them all over the world, pretty much wherever there's any kind of volcanic activity. And there's a few other places which are rather famous or perhaps infamous for having columnar joints and for being uncanny as a result. And one of them is the Devil's Tower in Wyoming, famously the site of the UFO landings in Close Encounters of the Third Kind. And these joints are enormous. They're several meters in diameter, and people like to climb them. In fact, it's quite a popular thing is to climb columnar joints. Another place which is in California is called the Devil's Postpile. You'll notice that the devil has been very active in making these things. They're always either described as being built by giants or devils or something like that. And I like to say this reflects the theorists' early ideas about how they were formed, okay? This one is just near Yosemite in California, and it's a national monument, so you can drive up to them and go and visit. They don't let you climb up this rubble here and touch them, but you can look at them anyway. Very recently, however, columnar joints were discovered in an even more interesting place, which is on Mars, in a place called Marte Vallis. I'm not sure how you pronounce it, but it's a huge crater. And the idea is that at some past time, there was a lava flow on Mars, which became columnar, and then it was excavated by a huge impact crater. And if I zoom up on this little area down here, you can be fairly convinced that these look like earthly columnar joints. And as I will describe in a few minutes, water is involved in the formation of columnar joints. So the idea that these really are normal columnar joints on Mars is quite exciting because it's partly evidence that there was water on Mars, yet more evidence for primordial water on Mars. These are deep under the ground, so they don't have to be water now. But at the time of their formation, they could have been water. For some reason, things that happen on Mars are suddenly vastly more interesting than things that happen on the Earth. I'm not sure why that is, but that's how it is. So I'm going to answer, I hope, some of the more obvious questions. How do these crazy things form? And what sets their size? And I will argue that the question of what sets the size of the columns is really the important question. And then I will hope to convince you what sort of tabletop experiment could possibly shed light on such questions. Now, the geologists have been spending several centuries working on this problem, and I will not describe all of the false starts and all the wrong theories, but this is the current understanding of how columnar joints form according to the standard textbook Geology. The columns are actually carved out. If you take lava and it's red hot and it cools, it will shrink. And as it cools and shrinks, it develops stresses, just like mud develops stresses, and those stresses can become large enough to break it. So as the lava begins to cool from the outside in, the outside gets gets stressed, and it cracks just like mud. And then as time goes on, those cracks penetrate farther and farther into the lava flow, and after a while, they've penetrated very far into the flow, and they get so far that it actually would take centuries for the heat to escape by diffusion alone. But what happens is that water gets down in these cracks and boils down where they're hot, and that carries out the heat. And that is such an efficient way to remove heat from the flow that determines the heat transfer fairly soon after the cracks begin to penetrate the flow. So what happens is a crack network develops on the surface of the flow, just like a mud crack network. And then as the crack network advances, it extracts heat from the flow mostly by boiling water up through the cracks. And then a region down near the crack tips advances into the flow. And down here, it's too hot for water to exist, and the heat travels down by normal heat conduction until it can find some water to boil off and be carried out. And one important fact is that these cracks do not advance slowly. They actually advance in little brittle advances, little sudden crack motions. And those crack tips advance suddenly, asynchronously on different cracks like this. Okay, so up here, it's basically all cold. Down here, it's all warm. And everything happens in a zone between those two. And as each little crack advances, it leaves a mark on the side of the column. And these marks are called striae. I hope I'm pronouncing that right. That's how I say it anyway. And so if you look at a reasonably fresh column, you can see it's marked on the side by these little horizontal lines. And this represents a fracture advance. Jump, 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 jump. And sometimes they're rather narrow, like this. I don't have a scale here. That's a piece of grass. And there's Lucas for scale, and you see these ones are very broad. Okay, now the reason you don't see these at the Giant's Causeway is simply that it's been exposed for so long, and it's all weathered off. So nobody noticed them on the Giant's Causeway. You have to see them on a fresh exposure of columnar joints. And there is no better place to find a fresh exposure of columnar joints than Iceland. So here is a picture sent to me by one of my Flickr buddies, and it shows spectacular striae on the side of a relatively fresh set of columns in Iceland. And they look like stacked books or something. But each of these things represents a sudden fracture advance. And you notice they don't quite line up with each other. They make a kind of wrinkly pattern on the surface. And those are the striae. And those are important to the story. Okay, so as the thing is cracking and advancing, it turns out after a while, this region where all the action is happening has some kind of scale L, where all the stresses are causing the fractures. And above that it's cold, and below that it's hot. And that little slab advances into the flow at a constant speed. And it advances at a constant speed because the water carries the heat to the surface. And it doesn't matter how far the surface is away. It's so efficient at carrying the heat out that it carries the heat out, and just this thing slowly moves through the lava flow, carving out the columns as it goes. And once it gets to all the way to the end, the whole thing cools down, becomes a solid, and eventually it gets eroded or something removes the top off it, and then you see it as an outcropping like the Giant's Causeway. So before we talk about how that happens in columnar joints, it's wise to go back and discuss some mud physics. I'm very interested in mud, okay? My kids know that every time we go out for a walk and I see mud, I look at the cracks very carefully, okay? So it turns out that it's actually rather tricky to get hexagonal or nearly hexagonal mud cracks. Everybody says, oh, mud cracks are all hexagonal, but that's not true. In fact, they are mostly square, and they're mostly bounded by T-shaped junctions and not Y-shaped junctions at all. So I want to make a distinction between sequential fracture and iterated fracture networks. This is a network of cracks. And these things, by the way, are called PEDs. That's a great Scrabble word, right? A PED. A PED is a little lump of mud, okay? See the wonderful technical terms that we have. So in sequential fracture, what happens is you have your whole layer is drying in this case and not cooling. As it dries, it shrinks, stresses develop, it cracks. And then you get primary cracks, which are things like this one. And then later, there's a secondary crack. And the secondary cracks feel a different, they're steered by the stress field of the first crack. And if they approach a primary crack, they'll turn and they'll hit it at 90 degrees. And you can show that this is the direction that it should go to maximize the release of strain in the material locally. And that gives rise to this, naturally, to this T-junction. So after you've cracked this thing for a long time, it naturally heads toward a pattern which is mostly T-junctions. So that brings us to the film. And I believe this is, in fact, the world premiere of Mary Miedema's movie, which is Watching Mud Dry. Ready? Roll. There's the primary cracks. Notice the secondary cracks come in very quickly. They meet the primary cracks at 90 degrees. After a while, the action slows down considerably. Nothing interesting happens. And there might be some tertiary cracks. There's a few little ones. The end. So let's... Mary is sitting right over here. I'll point my laser at her. There she is. So this is the pattern that you get at the end. And you might say, well, why doesn't it just keep going? It turns out that the scale of these cracks, the typical spacing of the cracks, is related to the thickness of the layer. If I make the layer thicker, the cracks will be farther apart. And there's a scaling relationship between those two. But if you look at this for a while, you see that mostly, really, they are very square. There's a few junctions that look a little bit Y-ish, but almost all of them are quite T-shaped. In fact, there's a kind of incipient Y there, all right? Okay, so if what we did is we're scientists, right? We can't just look at it. We trained a computer to recognize the shapes of the heads and decide how many sides they had and what their angles were and so on. And this was done a long time ago. But basically, most of them are four-sided after this kind of process. There's a few three-sided and a few five-sided, but there's relatively few hexagons, okay? The number of hexagons is actually pretty small. And if you look at the distribution of the angles that the things make, it's enormously peaked at 90 degrees. There's virtually nothing at 120 degrees. There's no Y junctions, basically. So the question is, how do we ever get hexagons? If I can't make them by a cracking process which obeys the normal statistics of cracking, how can I ever get them? Well, it turns out you can get them not sequentially, but iteratively. First, you make a crack network which has T-junctions and square heads, and then you wet it, or you cool it, or you warm it up and cool it, or you do something to repeat the cracking process, and you sequentially crack it over and over again, and it turns out that makes it move from T-junctions and squares to Y-junctions and hexagons. And here's how it works. And this is a beautiful tabletop experiment, which I have to say I'm very proud of, because I didn't think of it. Lucas, my student, thought of it completely on his own and did the experiment. And it's very simple. You start with a layer of mud, and you let it crack, and you get a network with T-junctions like this one. And then you just spritz it with water until it's nice and wet, and then you crack it again. And he's a very patient young man, and he did it for 25 iterations. It takes many hours to crack. And what you see is, this is the primary crack, and this is the secondary crack on this T-junction. But the next time it cracks in nearly the same place, but in a different order. So here's the first crack in this iteration, whoop, and here's the second one, ding, right? And then in the third generation, or maybe this is some other generation, the first one went this way, whoop, and then the second one came in that way. So after a long time, the cracks approach each junction from random directions, and that removes the asymmetry of the T, and all the directions are equivalent, so it becomes a Y. And in fact, it moves just a tiny bit in order to accommodate that. So this one moved from there to become something like a Y junction. And if you look at the statistics, you see that it does go from a peak at 90 degrees over to a peak at 120 degrees. Now, this does sometimes happen in natural mud, but it has to be natural mud that cracks, it gets rained on, and cracks and gets rained on again. And a great place to do that, to find such mud, is in Death Valley. And I've never been to Death Valley, but Bernie Halle has been to Death Valley, and he took his Swiss Army knife with him. And this is actually a natural mud crack pattern which has a lot of hexagonal joints, a lot of hexagonal heads and Y junctions, and it also has something else which tells you that it's iterated, and that is that the centers of these things are mounded up a little bit. And that's because every time the cracks open, a little bit of stuff, technically known as schmutz, falls into the cracks, and then when the cracks close up, they push the center up, you see? And they open and close many times, and they lever the center up like this. And that means the cracks are found in little valleys. So you can see here's a little Y junction that didn't reopen on the last cycle, and here's another one, you see? So if you see this, and you see hexagons like this, it's not because it cracked that way once. It cracked that way after many iterations. And there are other systems in nature where this happens, and Lucas had the good fortune to go to the dry valleys of Antarctica, which, contrary to your picture of Antarctica, are not covered with snow. They get very little rain and very little snow. This is just a little tiny dusting of snow. And what you get is what's called patterned ground or polygonal terrain. And this is caused by the freeze-thaw cycle rather than drying and cracking. It's got something to do with the fact that water expands when it freezes and contracts when it thaws, and those levering motions make cracks, and those cracks open and close every year. And this terrain is tens of thousands, or maybe even hundreds of thousands of years old, and after many, many iterations, the same kind of process occurs. Y-junctions emerge, and hexagonal, they're not called PEDs now, hexagonal tiles, or whatever you want to call them, appear. And what do you know? They're on Mars too, okay? Now, those ones I just showed you are a few meters across. These ones are a few hundreds of meters across, but it's believed that patterns like this on Mars are evidence for Martian permafrost-like behavior. And whether it's actually water ice or some mixture of carbon dioxide ice and water ice is a complicated question, but it's believed that these crack networks on Mars are also dominated by too many Y-junctions. Here's a sort of a hexagon, and this is evidence for a freeze-thaw cycle on Mars. An even more bizarre place where you might find such a process is on the snout of a Nile crocodile. It turns out that all the body scales of crocodiles are the same from crocodile to crocodile, and they're guided by the DNA and the usual developmental mechanisms, but the snout scales of a Nile crocodile, I love saying that, okay? The snout scales are different for every specimen, and that's because during embryonic development, they have a kind of crunchy layer develops, and as the animal grows, it cracks, and it's believed that there's a kind of iterated cracking pattern going on there, and people have analyzed the joint network on the Nile crocodile in this paper, and they claim that it evolves in a way that's similar to the thing that I have been describing. Okay, so what does this have to do with columnar joints? How does it work? Well, the things I've been telling you about now occur in a single layer where you repeatedly crack it. In columnar joints, that layer is not repeatedly cracked, but it moves and the cracks advance. And so this is a paper by Aiden and de Graaf where they found a place in Hawaii, which I really mean to go to, where you can see the bottom of the lava flow right here. And in fact, the lava flow cooled downward. The heat went down into the ground here, and the cracks move upward in this picture. And what you see is that there's a lot of cracks initially, and a lot of them stop, but there's also a lot of T-junctions initially. So there's a lot of T-junctions at the base of the flow. And as you look just a few meters up, you find they very quickly turn into Y-junctions. And I'm not sure this is some kind of intermediate thing. And they very quickly turn into mostly Y-junctions. So after just a few meters, the columns which develop from these cracks are mostly hexagonal, and they have Y-junctions instead of T-junctions. And this formation is called the lower colonnade. And typically the most beautiful columnar joints you get don't form from the cracks coming down from the top, but they form from the cracks coming up from the bottom. So for example, on Staffa, this is the great colonnade of Staffa, you see here's the grand colonnade, and the cooling direction is actually, the crack direction is actually upward, and the cooling direction, the heat runs downward. And up here you have something called the entabulature, which is a very disordered looking mass of very small columns, but it's very disordered. This rock is actually exactly the same as that rock. What happens is the horizontal flow cools from both directions, and the bottom cools by losing heat into the ground very slowly, and that develops the beautiful columns down here. And the top is cooled much more rapidly because it's exposed to the rain and so on, and it cools much faster, and that produces this disordered thing called the colonnade. If you look very closely, and perhaps I'm a true believer, but if you look very closely, you can see a kind of wrinkling down here, and it's not as smooth as it is up here. That's the little region where the columns adopt the hexagonal and Y-junction-y sort of shape. And after that, they just sail along. This little thing here, which looks like a garage, is actually, this is an old ash layer, which is believed to have been there before the lava came down. And this little cave here is called Boat Cave. And one of Bob Mayhew's great discoveries, and very brave thing, was he went into Boat Cave at low tide and established that it connected to the other side of the island and got out again before the tide came back up. That's why he's a spelunker, okay? And I'm not. So what Aiden and de Graaf did was they used the striae and what are called the Hackle patterns on the striae, or plumose patterns. If you look very closely on fresh striae, you can deduce how a crack front zipped around on these. As it moved very quickly, you can see the pattern left behind. And he established that various crack directions are possible. So for example, here's one where a crack came in and one went out and one went out that way. Here's one where one went in and one went in and one came out, and all the combinations are possible. So as the columns are carved by the advancing cracks asynchronously, they approach the junctions at random directions, just like in the mud, and that does the same job. It turns the T-junctions into Y-junctions, and that gives you the hexagonal columns. Okay, it's time to release the cornstarch. Okay, the experiment I'm going to describe is something that you can do in your kitchen, or you can almost do in your kitchen, and I encourage you to try it. We've done it many, many times. It's very cheap. You can go buy ordinary cornstarch, and all you do is wet it and then dry it out, and it cracks, and it makes beautiful columns. These columns are just a few millimeters across. What you do is you take cornstarch and you make a thick layer of it, not a thin layer like I was showing you before, but a layer that's several centimeters thick. These are centimeters. And then you dry it just with a hot light. It takes a long time, maybe days. And then when you break it open at the end, you'll see the whole inside of it is beautifully organized into these cracks. And the surfaces look just like the surface of the Giant's Causeway. Now, I didn't discover this. This idea was brought to my attention by a paper by Mueller from the 1990s, which was brought to my attention by Pierre Robin, who's sitting in the audience somewhere. So everything you're hearing about is basically because of one conversation I had with Pierre in which he told me about this paper. And we realized that we could do this experiment in a more careful way and learn more about it. And so we thought, if you read Mueller's paper, he doesn't cite anyone for this idea. So it sounds like it was his idea. But it turns out that it's really, really an old idea. It's mentioned, the fact that starch cracks into columns is actually mentioned by Thomas Henry Huxley, okay, who used to be called Darwin's bulldog. He was a famous kind of public scientist of the 19th century. And he wrote a book called Physiography, which is sort of an unfortunate neologism that did not survive, but it's basically the founding textbook of physical geography. And in it, he discusses volcanoes and lava, all sorts of landforms. And here on page 204, he says, oh, you can find, even volcanic outbursts in England. Especially in the county Antrim, where the remarkable scenery of the Giant's Causeway is due to the fact that some of the old lava has split up into columns, not altogether unlike those into which a mass of starch splits during drying. And then he says, oh, similar evidence of volcanic action can be found in Scotland, and blah, 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 blah. He doesn't say anything else, okay? This is extremely frustrating. How did he know that starch does this? How many people knew this? How come nobody did this experiment before? As far as we know, Mueller is the first person to publish a scientific paper exploiting the fact that Huxley knew since 1881. So, you're all going to go back and buy Huxley's book and look for good ideas that nobody's bothered to follow up on, okay? So here's the experiment that you can do in your kitchen almost. It's extremely high-tech. What you do is you get a beaker, you fill it with Canada brand cornstarch and water, about 50-50. You put it on a scale and you point hot lights on it and you go away for a week. And you come back, and when it's dried out, you analyze the cracked starch that you get. If you do that, we call that an uncontrolled experiment. We measure the weight of the starch, which tells you how much water there is in it as a function of the time, but we don't do anything else. If you really want to make the Giant's Causeway with starch, you have to control the rate at which it dries. So then we very cleverly get the computer to read the mass on the balance, and then we feedback control the lights to change the amount of heat we're putting on them to control the rate at which it dries. That's an experiment that you can't do in your kitchen. But, maybe you have a more high-tech kitchen than I have. Go for it. And the next high-tech thing is you take your 20 cents worth of cornstarch and you find somebody at the hospital for sick children who has a fantastic scanner, and you put it in there and you make a 3D X-ray tomography scan of it. This is a place called the Mouse Imaging Center, and they have this is a 40-micron resolution X-ray scan, and you get a 3D information about where the cracks are inside. You can also do this the hard way by shaving the thing off and taking pictures of it, destroying the sample as you do that, but it's far more fun to take it over to the hospital and just scan it. It takes a very short time. Okay, so this is an uncontrolled run, and what you see is that they look like columns. On one end are small, and the columns on the other end are kind of large. And so what happens in an uncontrolled run is that the scale of the column slowly grows, and the rate at which the mass decreases slowly slows down, okay? Because it's harder and harder to get the water out of the starch as time goes on, and that causes the columns to get larger, and I'll explain that. So here's a movie where we sweep forward using the X-ray scan in the direction of cracking. So this is sort of what the crack network looks like as it advances through the starch. Okay, we're not doing this in real time, but we're doing it after the fact. And so I want you to focus your eye on one of the columns, and you'll see that often a joint will stop, or maybe even three, a whole Y junction will disappear, and the column will suddenly find out that it's too big. Like here's one. And you'll see that it shrinks quickly down to be closer to its neighbors in size. Here's a big one that just formed. You see it shrinking down. And you can study the statistics of how the Y junctions appear from T junctions, and you can do everything you want. This is exactly what you cannot do with an outcropping like the Giant's Causeway. They will not let you tear it apart or X-ray the gigantic cliff, but you can look at every detail of the ordering process in this experiment. If you do a controlled experiment, that is to say, you keep the rate of drying constant, so the rate at which water is leaving the sample per unit time is kept constant, then you get very regular looking columns, and this is our little Giant's Causeway in the jar. The big difference, of course, is that this only takes a week. Lava takes centuries or tens of years or centuries to finish cooling, and these are millimeters instead of meters, so it's a tabletop experiment. Okay, so is starch really like basalt or really like lava, or is it just a coincidence that they look similar? One way to test the idea that they really are similar, and there are many other ways, but the simplest way is simply to compare the statistics. Do they statistically look similar? And, does the ordering process make sense? Ironically, one of the only ways to get statistics on columnar joints is to use the data of an Irishman by the name of, with the unlikely name of O'Reilly. Okay, and it turns out that O'Reilly had a kind of crackpot theory for the Giant's Causeway in the 19th century. But the good thing about O'Reilly was that he was a data man, okay? He spent 3 years at the Giant's Causeway surveying about 200 joints, and he measured the length and the angles of every single one of those 200 joints, and he made this map. And it's only a few meters wide and maybe 4 or 5 meters long. And his paper is full of crackpot ideas and a great big data table, okay? So ever since then, it's basically O'Reilly's data that's the best data around for looking at the statistics of the columnar joints. And that's from 1879. And what we did was we took O'Reilly's map and we colorized it, okay, using computer software, which O'Reilly was not able to use. His map is in black and white. It's actually colored in sort of India ink or something like that. And the green ones here are hexagons in the sense that they have 6 sides. And some of them are quite perfect, pretty close to being ideal hexagons. There's one and there's another one. But many of them are very unhexagonal. This one has 6 sides, but one of them is really short. Right? And there's another really short one over there. The sort of mustard color ones are 5-sided, and these are 7-sided. So this is a common thing, a pentaheptad defect. If these things were to exchange one side, they'd both be hexagons, and that would be an ordered area. But you see there are areas where lots of hexagons appear, but there are also areas where there's not very many hexagons. And in fact, only about half of the columns are 6-sided. And a very small fraction of them are really ideal hexagons. They're really close to being regular-looking hexagons. And there's quite a few funny ones. These are 8-sided ones, and the red ones are squares, that is to say 4-sided ones. And they had turned out to be important in our story. So what we did was we simply compared the statistics of the cornstarch experiment as a function of time or as a function of depth with the values that we get from O'Reilly's map. And what we find is for various statistics, I won't tell you what they all are, but this is the standard deviation of the angle distribution. This is the fraction of angles close to 120 degrees. And the dotted lines are the Giant's Causeway values, and the symbols are the depth, or if you like, the time that the cracks advanced into the starch sample. And what you find is that the Giant's Causeway is pretty far from being ideally ordered. There's a pretty broad distribution given by these dotted lines, but the starch starts out more disordered than that. It starts out more like a mud crack pattern than that, and then it evolves toward the Giant's Causeway values, and it basically plateaus at those values. And so it does not continue to become perfectly ordered. It's not getting more and more ordered. It orders for a while until it reaches roughly the statistical ordering of the Giant's Causeway, and then it sticks there. But it does not become static. It actually remains dynamic. Columns, appear and disappear, and edges move around. It's just that it stops statistically evolving. So this is what I call residual disorder, and it's actually, I believe, intrinsic to the dynamics of this process. It's not a mistake. It's really a feature. It's a real thing about the system. Now, one thing that O'Reilly didn't tell us, he told us everything about these columns, more than you'd ever want to know about these columns, but he didn't tell us where they are. Okay? He had no way to survey the Giant's Causeway to say where the columns were. So back in 2006, I went to the Giant's Causeway with my friend Bob and his wife Eleanor. These are the spelunkers. And Bob was actually the president of the Grampian Spelunking Society. And Alistair Kennedy is actually a history graduate student. Actually, he's a geography graduate student at the time. And he wrote a thesis on the history of the geography of the Giant's Causeway. And it's a very interesting read. But we decided that we would find these columns. So Bob laminated some maps, because of course at the Giant's Causeway it's raining all the time. Okay, and then we went on a search to find these things. There's 50,000 columns. We're looking for 200. How hard can it be, right? So we hit upon the following algorithm. Squares are real easy to see with your eye, because you can't tell a hexagon from a heptagon, but you can tell a square. And there's only a handful of squares in here. The red ones are the squares. So we walked along more or less in a row until Eleanor saw a square. And she said, and then you took the map and you kind of went, is that the square? And sure enough, we found square number 121. And there is the 8-sided one. It's rather rare for a square to be next to an 8-sided one, and sure enough, there is number 131 and number 121. And the most uncanny thing happened then. You're holding the map, you see the thing right below your feet, and all of a sudden, everything around you sort of locks in, because you can see it all on the map. And then just by taking a few paces, you could walk across the map, and then the map runs out, okay? So we ran around taking pictures of hundreds of these, well, almost every one of these columns, using little fridge magnet numbers to try and put their numbers on them. And this little tape shows the outline of O'Reilly's mapped area. It gives you some idea how small it is based on the whole. It's not in a secret place. It's in a kind of obvious place. If you're going to the Giant's Causeway, I'll tell you how to find it. Okay, I'll give you the map, and you can have a fun day looking for the famous column number 123 or whatever. Okay, so why are they hexagonal, or at least mostly, or half hexagonal anyway? Where does this come from? Well, where it does not come from is the one that everybody thinks it is. Everyone thinks, oh, it must be the hexagons are perfect, ideal shapes in some way. After all, they tile the plane perfectly. There must be some optimum, perfect tiling, which the process somehow approaches, okay? This is a completely wrong idea, because this is a non-equilibrium, a wide-open problem, wide-open thermodynamic problem. There's no need for this thing to approach some kind of ideal, best possible configuration. It would be equivalent to saying, oh, the weather, it keeps changing every day. Why doesn't it settle down, Can't it find the optimum perfect weather and just stay there? And that's ridiculous. It's never going to settle down, okay? The same with this problem. Each of these cracks basically responds asynchronously, all by itself, to local information. It uses the stress and the energy release locally to decide whether to crack or not to crack, and then it goes for it, right? And then it stops, and then somewhere else another crack starts. And they respond to each other's stress field asynchronously through long-range interactions like this, and they're not conspiring, okay? This is a perfect example of how globally order can emerge from local rules, okay? And this is a big theme in nonlinear science. Birds fly in beautiful flock formations, not because there's a chief bird that tells them all where to go. Each bird responds to its neighboring birds in a simple way, and the whole flock dynamics emerges from those interactions. Each bird doesn't know what the whole flock is doing. Here, the cracks don't know that they're part of a hexagonal lattice, and they don't care either. All they do is they do what they do, and this thing emerges. It's an emergent property. There's another fact, which is that, as I showed you, the T-junctions evolve into Y-junctions, and big columns shrink in area and small ones grow. And you can understand this because if two cracks are too far apart, they'll attract each other, okay, and they'll try to eat that big column up. If they're too close together, the ones that are on the other sides will pull, the stresses will be in such a direction that they can get more energy and they can crack better by going in that direction. So there's a tendency for big ones to get smaller and smaller ones to get bigger. And you saw that in the movie. And what happens really is they all approach a certain scale. The network is not random because the polygons are very close in area. They're actually pretty disordered in terms of number of sides. But in area, and the uncanny thing about them is not that they're all regular, but the fact that they're all the same size. And in fact, there's a theorem, which I won't go into details, but it actually requires a disordered tiling of the plane with random numbers of edges and vertices. As long as all the vertices, as long as all the joint connections are Y-junctions, and each tile shares one edge, each two tiles share a single edge, you can show by a very simple argument, which I won't give you, that the average number of nearest neighbors in such a lattice has to be 6. So it's not completely crazy that a random tiling of the plane would end up with an average number of 6. Now, this is not random, mainly not because they're uncannily regular hexagons, but because they have an uncanny regularity of area. And it's really the area, or if you like, the average separation of the cracks, which is regular here. And the six-sided, or the almost six-sidedness kind of emerges from this. Okay. So now I'm going to give you the argument. We can understand this by analyzing the similarity between the starch experiment and data taken at various locations, including Staffa by Lucas. The basic idea is the following. Both starch and basalt form under constant flux conditions. If I take out a certain amount of energy per unit time, a constant amount, then it follows that the average position of the cracks, or the position of that active front, has to move at constant speed because it releases a certain amount of energy per unit time, which is constant. If you take out that amount, it moves at that speed. Similarly, in the water, in the drying experiment, we take out a certain amount of water per unit time at a constant rate, and the cracks advance on average a certain depth as a result of that. So the flux is proportional to the velocity of the average velocity of the crack network advancing. And this just follows from conservation of energy. Now, this is where Mahadevan comes in, because he realized that if there's diffusion happening in the system, and both water and heat diffuse around in the vicinity of the crack tips, then there's a length that comes out just magically from the ratio of the diffusion constant and the flux. It's actually technically known as the Moens-Sikirka length, and it appears in other physics problems. There's really only one length in the problem, is what it boils down to. And this is actually scales the thickness of that active zone. So what that means is if I take out a lot of heat or a lot of water, then the active zone has to become thinner. Okay? So if J is big, D is a constant of the material, then L has to get smaller. And this is what sets the scale of the columns ultimately. A more technical way of putting that is to say that there's a dimensionless number. That's a number whose quantities, when you put them in there, have no length or meters or anything to them. It's the velocity of the crack advance times the scale of the columns divided by the diffusion constant of either heat or water. And that's called the Peclet number, and it's named after a 19th century scientist. And what we should find is that all columnar joints should grow near, no matter whether they're in starch or basalt, they should grow at a value of the Peclet number, which is the same. It's universal, okay? And I'll show you in a moment, we find that that value is about 0.2. Now, if the Peclet number were really, really large, that would mean that the cracks were advancing so fast that there was no time for the heat or water to diffuse around to smooth out the temperature or humidity field. If the Peclet number was really, really small, that meant that the humidity field or the water or the temperature field had plenty of time to smooth out, and the cracks wouldn't have any stress to drive them. So it turns out that this Peclet number has to be somewhere near 1 for this process to work, okay? If the cracks outran the temperature, or if they were too slow compared to the temperature, they wouldn't develop the stresses to move. So we know from general ideas that it has to be near 1, but the basic idea is that the scale is some dimensionless value of this quantity, and I will show you that that turns out to, empirically to be 0.2. Now this is beautiful because we can do everything in the starch experiment. We can measure the size of the columns, we can control the rate at which they advance, we can control everything and measure everything, so we can test this idea. Here's the fracture spacing in millimeters. This is the typical diameter of a column. It's only a few millimeters. And here is the fracture velocity. We can infer this from the drying rate. We can measure the fracture velocity, we can measure the drying rate, we can make a connection between those two. And the data are the experiments, and some of them are controlled and some of them are uncontrolled. And you can use either one. And the lines here are, and we also know the diffusion constant of the water, because in a separate experiment we can measure the diffusivity of the water. So we know everything. And if that theory that I just showed you is correct, then these should fall on one of these lines here, which are lines of constant Peclet number. So you see, roughly, they do. There's actually a little bit of hysteresis, which is interesting, which I won't go into. But somewhere between 0.1 and 0.2, 0.3, you get this inverse relationship. The faster you make the columns, the faster you make the fractures go, the smaller the columns you get. Now, the kicker is that we can also do this in the basalt. And this is considerably more difficult. What you have to do is put your climbing gear on and go up the cliff and measure as many of the striae widths as you can. And we have a very large database of striae widths on various columns all over the world. And it turns out that the ratio of the height of a striae to the width of the column is a constant. So big columns have wide striae, small columns have narrow striae. And it turns out from that single number, we can deduce the cooling rate of the fracture of the lava. And from that, we can deduce the average speed using some physics of the cooling of the lava. We can deduce the average speed of the crack advance. And that's what this value is here. And then we can also, of course, measure the spacing of the joints. And that spacing goes all the way up to 3 meters here. So these are really big ones, okay? And it turns out that the data is a little noisier because we don't know the diffusivity as well. We don't know D that well. But using data from not from the Giant's Causeway actually, but from Staffa and from various roadside places in BC and from places in the Columbia Basalt in Oregon, you can get the data, and they really do have this inverse relationship. There's a lot of scatter. But you can argue that they basically have the same, roughly the same Peclet number as the starch does. So this establishes the origin of of the thing. And it's very, very simple. That active zone, which is moving in and carving out the things, is just like a layer of mud. If it's thin, then the cracks are close together. If it's thick, then the cracks are farther apart. What determines its thickness? It's velocity dependent. It's a rate dependent process. The faster you cool, the thinner the thing has to be to have the right Peckley number. Okay? The thinner it gets, the closer the cracks are together and the smaller the columns are. It's that simple. It's very simple. It's just like a mud crack pattern, except that it's velocity dependent in the thickness. Okay? And this follows from such basic physics, and it took Mahadevan, who's a very, very good theorist, to basically convince us that this argument was really all we were saying with our complicated mathematics. And it boils all down to that one little formula that I showed you. That's the last equation in the talk. Okay, and I know this was a good idea because we sent it to Nature, and it was immediately rejected. Okay? I spent about a month trying to come up with that first sentence for the Nature article. The Giant's Causeway, the most famous site in the world, a World Heritage Site. It's got to go to Nature. They rejected it. Okay? Insufficient general interest. So then, of course, we sent it to Science, and it was immediately rejected. So we sent it to the place you send papers after they're rejected by Nature and Science, which is Post-Nature and Science, or Papers Not Accepted by Science, which is actually called the Proceedings of the National Academy of Sciences of the United States of America. And not only did we get it in there, but we got the cover picture, okay? And this is a tumbled millimeter scale basalt analog flow of ordinary cornstarch, and it's on the cover of the magazine. Okay, so I've told you what we know. Now I'm going to tell you a few things by way of closing, to tell you a few things that we really don't know and we don't understand. One of them is a remarkable thing that we discovered, or Lucas and I actually noticed it many years ago when I visited the Devil's Post pile, and I kept it in the back of my mind for about 20 years. I got to figure out why this happens. But Lucas eventually documented it more in the field. There are places, and this is one called Frenchmans Coulee I think it's in Washington or Oregon, and the columns here actually undulate. They kind of do this. Okay, so the cracks here are actually unstable to meandering. They're not just cracking straight. They actually undulate. Okay? And these cracks are actually, these meanders are actually much larger than a striae. So it's not just single striae making ins and outs here. It's many striae, about 10. And so the column scale, this column size, can also become unstable. And this is a very powerful piece of evidence that this is a highly non-equilibrium process. As you drive it harder, it's unstable to motion. Okay? It doesn't settle down at all. And that actually carves out these amazing undulatory columns, and the rock climbers love these things. And this rock climbing route at the Frenchmans Coulee, for some rock climberish reason, is called Party in Your Pants. I'm not sure why it's called that, but I suppose that's rock climbing humor of some kind. But what you see here is these beautiful undulations here. An even more spectacular example, which I really, really want to visit, is near the north coast of Turkey, called Boya Bat. And this shows you the power of Wikipedia. Just by surfing Wikipedia, looking for pictures of columnar joints, I discovered this place. And look at that! Okay? These columns are not just doing this, they're doing this. Okay? And these are the two modes of oscillation of neighboring cracks. In thin layers, it's known that they can either go together, or they can go antiphase like this. Okay? So somehow there's an instability of the crack network if you push it hard enough, and it not just carves columns, but it carves wavy or undulatory columns. Okay, well, I more or less reached the end. I would draw your attention, those of you who are lucky enough to be American Physical Society members. Next month, I tried real hard to get it to come out this month, but it's not going to come out next month. We have a cover article about all this in Physics Today, that wonderful trade rag of our field. And this is my picture of the Giant's Causeway columns. And this is coming next month in Physics Today. Tuzo says, be quiet. So I'm finished. Thank you very much for your attention.